you go to the next slide, you see that around the entire northern hemisphere, spring is arriving 1 to 2 weeks earlier in the year. Wherever you are, trees are flowering earlier, flowers are flowering earlier. We're seeing all these kind of changes in the natural environment. On the next slide, you'll see that we're also seeing shifts in many of our iconic crops and plants. Maine blueberries are famous, but in the last decade or so, the center of blueberry production in Maine has already shifted across the border into Quebec. So pretty soon we're going to have to be calling them Quebec blueberries. If you go to the next slide, our extreme heat, our record high temperatures and our heat waves are twice as frequent now as they were in the last century. Next slide. We're also seeing all kinds of effects of climate change on our agriculture and drought. Since the 1980s, a colleague of mine at Stanford has estimated that we have experienced worldwide crop losses of $5 billion per year that are directly related to climate change. That's $5 billion every year since the 1980s that can be attributed to changes in climate. And then lastly, on the next slide, we're also seeing all kinds of pests moving north. We've got less cold days to keep the red fire ants at bay, or even kudzu. Kudzu used to be known as the vine that ate the South, but now kudzu is already well established as far north as southern Illinois, and the very first instances of kudzu were observed in Ontario, Canada this year. So pretty soon it might deserve the name of the vine that ate the whole country, the whole continent. So all in all, if you go to the next slide, we have seen responses to warming temperatures in more than 26,000 physical and biological systems around the world. From plants and trees to crops and invasive species, we have seen these changes 26,000 independent lines of evidence around the world that our world is changing. If you go to the next slide. So okay, we've seen how the world is changing. But the next question we need to ask is, are these conditions unusual? Are they something different than what we're used to seeing before? Or is it just one of those natural cycles that's just going to go back to where it used to be if we give it 10 or 20 years? Well, how do we figure out if these conditions are unusual? The way that we do it, if you go to the next slide, is through using what I call natural thermometers. Our own thermometer record, the very oldest one, goes back to 1659. But our civilization has been around a lot longer than that, and we've been keeping records in different ways. So, for example, people have been painting pictures of the glaciers in the Alps for a very long time. And if we know where those pictures were painted, then you can use them just like those photographs that Gary Brash used to compare to what it looks like today. In Japan, the Cherry Tree Festival is very important. It's so important that in Kyoto, they've been keeping a record of the date of that Cherry Blossom Festival for over 1,100 years. And we can see that the date of that festival goes up and down from year to year, but over the last few decades, it is far earlier in the year than it ever used to be, going 1,100 years back. We can also use other kinds of natural thermometers. There's my husband down the lower right there in Muir National Woods, or Muir National Monument in near San Francisco, and he's pointing at a tree that is nearly 1,000 years old. With trees, every year they produce one ring, and the width and the density of that ring gives you information on what the relative temperature and rainfall was in that year. And so you start at the outside and you count your way back down into December, going back in time. The oldest tree ring data that we have, putting together living and dead trees at the same location, are from the White Mountains of California, going back nearly 9,000 years, just with trees. With ice cores, we can go back even farther. The longest ice core in the world goes back 800,000 years. And it's very like tree rings. You start at the top and you count down the levels. You might not get a layer every year. If it doesn't snow very much, you only get a layer maybe every few years. But again, you can count back in time, and from these ice cores, you can look at the gases that were trapped in these little bubbles in the ice core. It's basically like a snapshot of what the atmosphere was like when that layer was formed. It tells you about the levels of greenhouse or heat-trapping gases, and it also even tells you about the temperature. Now, it doesn't do that by actually measuring the temperature, but how it does it is because it traps the ratio of one type of oxygen to to another. And that ratio tells you what the temperature was like when that ice was formed. And then you can get information from all kinds of other sources like stalactites and stalagmites and caves or boreholes or all kinds of different natural thermometers. So what do we see when we put all this information together with our thermometer record from the last 150 years? Well, if you go to the next slide, you see that our conditions today are very unusual in the context of the last 2,000 years. So in terms of Western civilization, we've experienced periods like the medieval warm period and the Little Ice Age. And we see natural climate variability going up from year to year, up and down from year to year, or even from decade to decade. But the temperature today has increased far more rapidly, and it is far above any temperatures that we've seen over the last 2,000 years. So what we're looking at here is very, very unusual. Now, sometimes there is a graph doing the rounds that someone might wave at you one time that shows that the medieval warm period was the same temperature as today. And so people say, look at this figure. It shows it was the same temperature, so it's nothing to worry about today. Well, how did they get that graph? It's the same type of cherry picking that I talked about back at the beginning. There is one location in the Sargasso Sea that was probably just as warm in the medieval warm period as it is today. But the Sargasso Sea is not indicative of what's going on around the entire world. You need to look at the average over the whole world, or at least the whole hemisphere, not one single location. So the truth is that what they call the hockey stick graph, that's what you're looking at right here. They call it a hockey stick because there's a long flat area and then it goes straight up at the end. The science underlying the hockey stick is very robust. And what it tells us is that it's very unusual, what we're seeing today. If you go to the next slide, you say, well, what if we go back farther? This slide goes back 6,000 years. Are there any major natural cycles over the last 6,000 years? Well, what we see is that, in fact, no. There are no very large natural cycles that we've seen over the past 6,000 years. All we see is a gradual, slow decrease in temperature right until the Industrial Revolution. And that is when we figured out how to dig massive amounts of coal and gas and oil out of the ground and burn them, releasing carbon dioxide into the atmosphere. So it's no surprise that we see carbon dioxide levels going almost straight up after the Industrial Revolution, and we also see temperature following those carbon dioxide levels. So it's really interesting because a lot of people, I forget the exact stats, but a very significant proportion of people living here in the U.S. Believe in a relatively young Earth, between 6,000 to 10,000 years old. Well, here's the thing. If you believe in a young Earth, you cannot argue that the changes we're seeing today are because of natural cycles, because there are no major natural cycles over the last 6,000 or 8,000 years. They just aren't. Well, but what about, if you go to the next slide, why is this happening? Well, contrary to what a lot of people think, scientists don't immediately rush into saying, oh, it's humans, we'll just close the door, we don't have to look at anything else. No, we have looked at every other reasonable explanation for why this is happening. And the first, what I call the first usual suspect, is our sun. So if you go to the next slide, what this shows is the energy that we get from the sun and how that's been changing over time. That's the purple curve. The blue curve shows how active the sun has been over that same time period. And then the orange curve shows the Earth's temperature. Again, this goes from 1875 here to about 2006, I think. So what you see is over the first part of the 1900s, we were getting more energy from the sun, and the sun was more active. But all of that peaked in about the 1970s, and since then, we have been getting decreasing amounts of energy from the sun. In fact, right now, we're in a solar minimum period. But at the same time that the energy from the sun has been going down, our temperature has been increasing faster and faster. So changes in energy from the sun cannot explain our warming. In fact, we would be warmer than we are right now if it wasn't for the sun temporarily helping us out. Well, so if it's not the sun, what about the next usual suspect? What about natural cycles? Well, we've already talked about how the fact that we don't see any major natural cycles over the last 6,000 years. If we're going to argue natural cycles, we have to go back a lot farther than that, which is the next slide. What this slide shows is the temperature and the carbon dioxide levels obtained from the oldest ice core we have, going back 800,000 years. And we see that in the past there have been some very large natural cycles, with the Earth's temperature going up and down by over 10 degrees Fahrenheit, and carbon dioxide tracking that cycle. But here's the thing.
Oh, I'm tracking a presentation on that.
Oh, you are? Okay. Did you have a question?
No, sorry.
Okay. But what we see, though, is that our current conditions are actually far outside the range of even those natural cycles. In terms of our temperature, we're at the very top of the natural cycle temperature range. But in terms of our carbon dioxide levels, we are far above. In the past, carbon dioxide has gone up and down from about 150 to 300 parts per million. And right now, we're almost at 400. So what we see today looks nothing like the natural cycles of the past. No, the explanation we have to look for is the next slide, which is this. Our planet has something called the natural greenhouse effect. And the natural greenhouse effect keeps our planet almost 70 degrees Fahrenheit warmer than it would be otherwise. It's basically like a blanket around the Earth that traps the Earth's heat and keeps it a lot warmer than it would be otherwise, just like our blankets work at night for us. So this natural greenhouse effect has nothing to do with humans. But what we are doing is we are enhancing it. We are artificially increasing the natural greenhouse effect by putting more and more abnormally large amounts of these heat-trapping gases into the atmosphere. And just as you'd expect if somebody snuck into your room at night and pulled an extra blanket over you, the Earth is heating up because of this extra blanket that we have put on it. Where does this extra blanket come from? Well, if you go to the next slide, we know that every time we burn coal or gas or oil, it produces carbon dioxide. That's those colored areas there. And we can measure how much of that stuff we've burned since the 1800s. We can also measure what the levels of these gases have been in the atmosphere. And no surprise, we see that the more fossil fuels we burn and the more carbon we produce, the higher the levels of carbon dioxide in the atmosphere. Where does this come from? Well, if you go to the next slide, you'll see that these gases come from our factories, our cars, heating and cooling our homes, and other gases like methane even come from agriculture, like cows. Cows produce a lot of methane. About 90% comes out the front end, and about 10% comes out the back. Who is responsible? Well, if you go to the next slide, you'll see why this is such a tricky political issue.